All right, I think it's time. Welcome back to everybody. I hope you're surviving and thriving. We do have homework due tomorrow night, so check it out. It's due on Gradescope sometime, tomorrow before midnight. Please let me know if you have any issues with the Gradescope, and if you, if the homework is like due and for whatever reason the Gradescope isn't working for you, that you can just email it to me in case of emergency. Anybody got questions about any of those? All right, let me know if questions come up. I'd be happy to chat about it. Just to remind you of what the rhythm is like for our class. We got the homework will be due on Wednesday. The homework is about the first two topics on our big list, just sort of like basic derivatives and integrals, and also the U substitution. And then on Friday, we will have our first quiz. It will have two questions on it. One will be about basic derivatives and integrals, and the other will be about U substitutions. We'll just do the quiz for the first 10 minutes of class or so, and then go on with the rest of class immediately. If you have accommodations for extra time on tests and quizzes and whatever, please let me know, and we should discuss. We don't have to talk right after class, but at least send me an email because the way I like to do the quizzes, just right at the beginning of class and then immediately continue with the rest of class, this can be hard to manage if some people are taking more time than others. I mean, it's no problem. We just need to talk about it. So let me know. We'll talk about it. All right, great. Let's talk a little more about area between curves, and then we can go on to something else. I just wanted to do one more variation on area between curves. Sometimes you need to do integrating in terms of y. I sort of started talking about an example like this at the end last time. I want to finish that example, and then I have one for you all to try. There's not a lot to it. You just have to kind of know what's up. So this is an example where the two curves, one of them is a line. You should see this in your notes from last time. And the other is a sideways parabola like this. So the line, that's the line. And the parabola is x equals y squared minus 3. All right? And because of the sideways parabola, which is not a function, this is the area I'm talking about. The fact that this is not a function, meaning the vertical line test is not satisfied, it means that you can't do the top minus the bottom, which is what we usually do when we're doing the area between curves. Top minus the bottom will not work. Over here, there are some points over here where the top and the bottom are actually the same curve. And if you use the equation of the top curve minus the bottom curve, it's the same curve, and you're going to get 0 when you subtract them, which is not correct because there is real area there. It's not 0 area. So anyway, when you have something which is not a function, you must instead integrate in terms of y. So we are first of all going to write all the curves like x equals whatever in terms of y. Right? X equals whatever. Usually the curves are given to you solved for y, but in a situation like this, we need to solve them instead for x. Now, one of these is already solved for x. It is x equals, come on now, x equals y squared minus 3. But the other one says y equals 1/2 x. This, when I write it the other way around, I would multiply the 2 onto the other side, and it will say x equals 2y. So those are my two functions, all right? And we are going to integrate them in terms of y. Now, just like before, we need to set up this integral using the two intersection points here and here, right? Those are the 2 points which define sort of the boundaries of the area between the two curves. So we have to find the intersection points. Sorry, my pencil is acting up. we find the intersection points, as usual, by setting the two equations equal to one another. So all of this is going to be in terms of y this time, but I'm going to say 2y. Come on. I don't know what's going on with this thing. Oh, it wasn't screwed in good. Oh, yeah. 2y equals y squared minus 3, right? You set the two curves equal to one another, and now we have to solve for y here. This is a quadratic, so I'm going to put everything on one side and then factor. Everything on one side set equal to 0 and factor. Maybe I'll just put it all on the right side, because I like the y squared to be a positive coefficient. So it'll say 0 equals y squared minus 2y minus 3, right? And then I'm going to factor. That's this thing. Any factoring masters out there? What do you get for the two factors? Yeah? Y minus 3 and y plus 1. I like that. Remember, these two numbers, their product should be this, -3, and their sum should be -2. So it's like that. And now this means, you set each one equal to 0, so y minus 3 is 0, which means y is 3, or y plus 1 is 0, which means y is -1. So these are my two intersection points. You should be able to look at the picture and kind of verify if that looks reasonable to you. There are two intersections. One has y equals -1. That's here, apparently. And the other is y equals 3. This actually looks pretty good to me on the picture. -1 and 3. All right. And now I think we are ready to set up the integral. All right. We always do, traditionally, when we're doing in terms of x, it's the integral of the bigger minus the smaller. Now, in the case of a sort of a sideways thing here, I'm talking about bigger means further to the right and smaller means further to the left. So here I'm going to do integral of, it's always biggie minus smalls. But in this case, it would be bigger versus smaller in terms of x value. And the bigger x value is to the right. The smaller x value is to the left. So this is actually sort of the right side minus the left side. When we're doing it in terms of y, instead of tops and bottoms, it becomes rights and lefts. So it is the right side minus the left side. But anyway, we've already done all the setup here. It's going to be look at the two curves. Which is the curve on the right side of this shaded area? It's the straight line. So the one on the right is 1/2 x, which is written this way, 2y, right? I'm doing all of this integration in terms of y. 2y minus the other one was the parabola part, y squared minus 3. And it's a dy. All right, this is the integral in terms of y. And we need the boundary values, but they are the numbers that we already found for the y. It's -1 and 3. You always put the smaller number on the bottom. So it's -1 to 3 of that stuff. And then from here, you just do the integral as always. I would distribute the minus sign. This, from this point, is a pretty straightforward integration. Distribute the minus sign like that. And then I'm going to do the antiderivative. 2y becomes y squared. Minus y squared becomes minus 1/3 y cubed. And then plus 3y. And I plug a -1 and a 3. And then you plug them in. So the 3 first, and then you subtract the -1. So this is my answer. 3 squared minus 1/3 3 cubed plus 3 times 3 minus, and then plug -1. -1 squared minus 1/3 minus 1 cubed plus 3 times -1. There you go. This is the area between the curves. All right. Any questions about that one? This is how we do it. Really, it's the same as the ones we were doing before. It's just everything is y's instead of x's. All right. All right, I got one for you all to try. How's about find the shaded area? I got a line here. This is y equals x plus 1. And then I got a parabola here. This is x equals y squared. And I want the area, this here area. All right. This time there are no intersection points, so you will have to figure out somehow by looking at the picture where are the boundary values. The y goes from here up to here, but I'll let you consider those questions. All right, see what you think. I'm going to come around and see how you like it, how you like me now.
The purpose of these intersections is really here you need to just find some of the
Okay. All right. Picture.
So you want to find the intersections. The purpose of those intersections is to figure out sort of the numbers. So you can figure that out. So you can just set up the number immediately. You can run a right function, a right function. You should solve them both. It's not so just like yeah, my friends should yeah, but it's not if that's finding intersection points. Yeah, yeah. The point of being not setting equal in your case, no. It's like how's it going? Yeah. This actually you don't need to do this step in this one because this is for finding intersections to get the two curves, but they don't intersect. How's it going there?
Think about it.
Yeah. Maybe
Just go for
there should be parentheses here.
5 hours.
So then actually that minus. No problem. You do the integral.
Doing okay here? It's actually this step is not necessary. Here we did that. But here there so you can just set up these ones.
The final score was 70.
You look past it. But here you could tell. They doing all right over here? Yeah, something like that. Well, I don't like this. I think you messed up the numbers, but it's still flipping all. Yes. Yeah.
But then he doesn't play as and say we play.
I'd say because the y side is the bottom.
It's 40. Well, it's not numbers like that. It's you have to get to fix that. That's when you put the gate and you're 7 games.
Am I right here?
Yes.
Yes.
So it's deuce, right? And then you win the next one. So if it was one it's added you.
All right, folks seem to be doing pretty good here. Some people were kind of got a little meandering when it came to starting off by finding the intersection points. That actually is not necessary in the problem that I was asking you to do. Here you need these two intersection points so that you can tell the bottom end of this figure is at y equals -1 and the top is at y equals 3. But in this one, this is actually an easier one. You don't need to do any work. I can tell just by looking that the bottom here is at y equals 0 and the top is at this y-intercept, whatever that is, but you can tell here it's +1. So here the integration, the boundary values here are 0 up to 1, right? And you don't need to do any like algebra to figure that out. You can just tell by looking at the picture here. So you can more or less immediately set up the integral, although I do need to write them both in terms of x. So I will transform this into x equal y minus 1. And the other one I leave as x equals y squared, right? But then I can just immediately set up the integral as the one on the right minus the one on the left. And in this example, the one on the right is the parabola, the one on the left is the line. So it's going to be integral 0 to 1. That's because this shaded region, at the bottom it has y equals 0, and at the top it has y equals 1. And then I go the one on the right, y squared, minus the one on the left, like that. dy, not dx, dy. All right? This is the setup. And then from here, you just do the integral. But I hope that in these problems, this is kind of like the more important part of it is understanding how to set it up. Y minus 1 in parentheses. I hope you remember the parentheses there. You're going to have to distribute the minus sign. So really this is y squared minus y plus 1, like that. And then the antiderivative would be 1/3 y cubed minus 1/2 y squared plus y, like that. And then we plug in 1 and 0. When I plug 1, all those y's, powers of y's are just 1, so it's 1/3 minus 1/2 plus 1. And then I plug in zeros, and I just get zeros every time. This is 5, 6. I saw some I know some people are like compulsive simplifiers. It's okay. We've all been there. If you insist on simplifying, it is 5, 6. I'm not much of a simplifier, but all right. Any questions about that one? I hope it worked out. I mean, I know it worked out for most of you. All right, here ends the discussion of area between curves. This was just one sort of leftover example from last time. The area between curves. Sometimes you have to do it in terms of y rather than in terms of x. And the tip-off, or like how you know that you should do it in terms of y, is because one of the curves is not a function. It's has this weird vertical line property. In that case, you have to do them in terms of y instead of x. All right, great. Area between curves was the first of our kind of using the integral to figure stuff out geometrically. The area between curves is one thing. I want to talk about our next two topics are about volumes. So using the integral to find volumes. All right? The integral is usually used to find the area of something or other, but you can actually use the integral to find the volume of certain 3D shapes. Weird looking shapes. For example, the typical shape is what we are going to call volumes of revolution, which always strikes me as a weird terminology, but this is what everybody calls them, the volumes of revolution. It sounds like a power ballad compilation album or something. Volumes of revolution. This refers to a shape, finding the volume of a shape which is obtained by revolving something or other. So the idea is I have a curve like this. Let's say this is f of x, from a to b as usual. And if I just do the integral of f of x, that gives me the area under the curve. I would like to somehow, instead of finding that area, I want to find the volume of this shape, the shape obtained by revolving this around the x-axis in a circle. All right? You get this sort of cocktail dress kind of shape sideways. All right? And I would like to find the volume of that shape using the integral. So it's not just the integral of f of x. That would give me the area of the top half of that. But can we find the volume of that shape? All right? This is called a volume of revolution because it is the shape which is obtained by taking a curve and revolving it around the x-axis. There are lots of shapes in real life which have that kind of property. Like any kind of shape you can make on a pottery wheel or a lathe or something like that will be a shape like this. And such shapes you will be able to find their volumes by using the integral. All right. Now let's talk about. There's a formula for this, of course, which eventually I'm going to tell you to memorize the formula. But I want to talk a little bit about where the formula comes from. The idea here, just like for the area under the curve, is the basic idea is make, I will say, skinny slices. This is always the idea behind the integral of an area. You slice up the area into little rectangles. This is not an area with rectangles, but it's a similar idea. So I'm going to try and draw that shape again. I'm not a great artist when it comes to drawing 3D shapes, but here I am going to, once again, slice this shape up in sort of a three-dimensional little slices. If you can imagine chopping this, like you would slice a cucumber or something. You cut it up into little bitty slices. And just like when I do the area using rectangles, I'm going to call the width of each slice delta x, just because I like calling little bitty widths delta x. All right? It's like the area using rectangles, only instead of rectangles, I'm slicing these kind of three-dimensional. Actually, can anybody say what is each slice? Each slice is a. How would you describe those shapes? Like an area that you cut up, you make rectangles. What is that, though? This is a three-dimensional kind of a thing. Could you imagine grabbing one of these? Well, how would you describe it?
Cylinder.
It's a cylinder, yeah. This is actually, if I were to draw it, I would draw it sort of like that, right? You might call this like a disc, like a wafer or something, like a disc or something. I already said that. It's like a disc, right? But actually, this is also a cylinder. Usually when you think of cylinder, you don't think of it like this. But if instead I were to draw it sort of lying down. Here it's kind of like standing up on its end. But if you draw this kind of lying down, it looks like this. And that is a cylinder, just like a very short cylinder, right? This is, the slices here are cylinders. They're cylinders that are very, very short, right? And the height, if you think of it this way as a cylinder, the height of the cylinder is delta x. And, you know, I intend to find the volume of this, so I would like to think about the volume of this cylinder. The height is delta x. It also has a radius measured across, you know, from the middle to the outside. So the slices are cylinders, the heights are delta x. I mean, when you draw it sort of lying down, it has a little height, or maybe I should just call this the thickness to be a little more clear. The thickness, I've been instructed I should write it this way without the C, right? Is that right? You don't write the C. Yeah, the thickness. The thickness is delta x of each of those little slices, and then it has a radius. Can anyone say, like, considering the original picture, where does the radius come from? The radius would be the distance from the middle of this round thing out to the edge. Yeah? It's the y coordinate. I think I'm not sure if is this what you said? It's this. That's the distance. That's the radius, right? Like this radius right here. If you look at it where that came from on the original picture, it's like the height of this thing, right? Wherever your slice is made, it's that distance is the radius. And what is that y coordinate? It's given by the function. So the thickness are delta x, and the radius is given by the curve f of x. All right. It's not two k's, it's two c's, right? I'm going crazy here. I should have prepared for class more. The thickness, two c's, yeah. Feel free to correct me, by the way, if I ever have a typo. The thickness is delta x. The radius is f of x. All right, so the total volume then, this is always how we handle things when we are doing these geometry problems by slicing up. The total volume is the sum of the slices in the limit as delta x goes to 0, right? Just like the total area under the curve is the sum of all the rectangle areas. And the rectangle area, of course, is the base times the height. Here we need to know what is the cylinder volume. So each slice cylinder volume there is a volume, there's a formula for the volume of a cylinder that I'm sure you all knew at one point in your life. Anyone actually remember this formula? If you have a cylinder which has a certain height and a certain radius. Anybody remember this formula? I don't actually care if you remember this formula or not, but we do need to use it right now. Yeah?
Pi r squared h?
Yeah, it is pi r squared h. Pi r squared would be the area of the circle, and then you multiply that area times the height, and you get the volume. So the volume here is pi r squared h. All right, so each slice has a cylinder volume. So the slice volume will be pi r squared h, but the h, I said already, the h is the thickness, which is delta x. So this is pi, well, I'll write pi r squared h, but plugging in our business, r squared is f of x squared. That's because, remember I said the r on our little slices is actually given by the height of the curve, the function. So pi f of x squared, and then h, the h of our little slices here is just delta x. All right. Those are the volumes of the individual slices. So the total volume would be the sum of all of those. So the total volume is what we get when we do the sum of all these things. And you take the lim as delta x goes to 0, right? But that is a Riemann sum because I have some stuff times delta x, and I'm taking the delta x going to 0. Since this is a Riemann sum, I can write it instead as an integral. And this is kind of my final answer. It's that. This is the formula for the volume of one of these revolved shapes. It comes from doing the cylinder volumes and adding them all up. All right, but I'm going to write this as a formula here, and this you should, I suppose, memorize. It's not much of a formula, but you do need to know this formula. So the volume obtained by revolving f of x around the x-axis from x equal a to x equal b is, this is the formula. Now, what I wrote up there is the integral of pi inside. The pi is a constant, and so when I do this, I'm always, you can always pull a constant out of an integral whenever you want. So I'm going to write it with the pi on the outside. Although you could write it with the pi on the inside. It's the same. F of x squared dx. This is the volume of revolution formula. And you need to remember this formula. It's not a lot to it. And I mean, in my opinion, it's pretty easy to remember. This is basically just pi r squared, where the r is the f of x. And you put that whole thing inside of an integral. All right. Why is it pi r squared? It's because the individual slices that you make are basically circles with a tiny thickness to them. And the area of a circle is pi r squared. So that's my very vague idea about why this formula is correct. If somebody on the street asks me, why you got to square that thing there? And I say, it's because it's like pi r squared. If you didn't square this, if there was no 2 there, this would just be the area under the curve f of x. This is not what you want, though. You want a volume of something, you square it to get the pi r squared. All right, this is the volume of revolution formula. Let's try some examples. All right, the examples of this are usually pretty straightforward, just like the area between curves. The hard step is, setting it up properly. How about, let's find the volume of this shape. I want the parabola y equals x squared, and just over to x equals 1, and I want to spin this around the x-axis. You get sort of like a trumpet kind of shape, a horn, if you will, like this, right? This sort of horn kind of a bugle sort of shape. All right, and I want the volume of that. This is an easy one. Pretty much all you got to do is plug into the formula here. There's not much more to say about this. I will do pi, because there's a pi in the formula. Integral a to b. Can anybody tell me what the a and the b are? The a's and the b's, on a typical example, they are, sorry to scroll away, they're these sort of the left end and the right end of the shape you're talking about. So what do you say for the a and the b here?
0 and 1.
Yeah, it's 0 and 1. I didn't really say 0, but you can tell by looking, that's 0 over here. And then I specifically told you it's 1 over there. So this is integral 0 to 1. And then I go f of x squared. So f of x in this case is x squared. But then I got to square it again, because that's part of the formula is squaring it. And then dx. And that's all there is to it as far as the setup here. All right? Let's actually do the integral. How do you handle squared? You should, in that situation, multiply the exponents. That's how you kind of simplify that on the inside. So this says pi integral 0 to 1 x to the 4 dx. And then we can just do the integral. Integral x to the 4 is 1/5 x to the 5. So I get pi 1/5 x to the 5, and I plug in 0 and 1. 1/5 1 to the 5 minus pi times 1/5 0 to the 5. That's 1/5 times pi, I think, is the whole thing, right? The other stuff is just 0. Pi over 5, if you like. Right? This is the volume of that bugly thing. Pi over 5. Strange, but true. Any thoughts about that? This was an easy one. How about, let's try one that's a little less easy. How about, I would like the area, no, the volume of a sphere with radius 2. All right? The volume of a sphere with radius 2. Now, this is another one of those things that you probably, well, I'm sure you did learn at some point. There's a formula for the volume of a sphere. So you could just plug into that formula and get the answer. I want to try and sort of work this out with our bare hands without using that formula. And actually, this method that we're doing here is sort of where that formula comes from. At least this is one way that you could derive that formula, even if you didn't know the formula ahead of time. But could it maybe just like in a box here, I will just remember the formula. Anyone actually remember this formula? Again, I don't care if you remember this formula or not, but anyone happen to remember it? I know there's some people who love remembering formulas like this. I have a hard time remembering things. You remember it?
I don't know if he's right, but 4/3 pi r.
It is. Yeah, that's almost right. 4/3 pi r. There's actually one more little thing. Anyone? It's cubed. Yeah, this is a volume of something, so you might expect there to be a cube of something in there. Yeah, this is the formula for the volume of a sphere. Like I said, I don't care if you know this formula. But in this example, the volume of a sphere, if I say the radius is 2, then the answer will be 4/3 times pi times 8. That's 2 cubed, which I guess, like whatever that is, that's 32 over 3 pi. I'm just writing this out because I want to check my answer when we eventually do it. Did I do that right? 4 times 8 is 32, yeah. This is 32 pi over 3. That's the answer that I'm hoping to get when we do it kind of by hand as a volume of revolution, all right? That was just a little aside. This is where we're going. If we do it right, I want to be able to check my answer. 32 pi over 3. Anyway, how can we look at this as a volume of revolution? It means you need to start with some curve, which when you spin it around, it gives you a sphere. Anyone have an idea of what curve can I start with? Like in this case, I started with a parabola, and I spin it around and I get this bugle thing. What kind of a shape do I need to start with so that when I spin it around I get a sphere? Any ideas? Yeah?
Circle.
Yeah, I think like a half circle here, a semicircle. If I start with just like the equation of the top of a circle, and apparently since I'm aiming for the sphere of radius 2, I want a circle of radius 2, right? I guess it goes back to minus 2 over there. All right, this is the circle with radius 2. That's what we should start with. And then when we spin this around the x-axis, it will create the sphere, which is what we're looking for. And one last sort of, do you happen to remember this formula? This one you probably, I think I would expect you to know. Anyone remember the formula for this curve here? This is a, I'm looking for the equation of a circle. This is the circle around the origin of radius 2. Remember how to do that with equations or whatever? Surely this is something that you learned in your youth. Anyone remember? Yeah? What do you think?
2/3 pi r.
This is something else. I'm looking for an equation of a circle. You know, something like, I mean, this is not it, but, you know, like y equals mx plus b, that's the equation of a line. What's the equation of a circle? That's what I want to know. You remember?
Y equals x squared, or negative x squared plus 2.
That would be a parabola that looks kind of like that, but I don't want a parabola. It's something, did you have an idea?
It's pi r squared.
No, that's the area of a circle. I want the equation of a circle. This is something like the equation of the unit circle. I guess nobody remembers. The equation of a unit circle would be x squared plus y squared equals 1. Remember that? This is the equation of a circle in the plane. I don't want the unit circle, though. I want the circle with radius 2. More generally, it's this. X squared plus y squared equals r squared. This, I said you should know this. I would say like this is like generally in life you should know this, although I don't know if this is actually going to come up very often in our class. All of these things I would put under the category of things that I wouldn't expect you to have memorized, but you should know where to look for them. Like if this came up on the homework, I would expect you to be able to remember, oh yeah, there's a formula for that, and then go find it somewhere. All right. Anyway, x squared plus y squared equals r squared. In our example, r is 2, so this is x squared plus y squared equals 4. That is 2 squared. All right. And one last thing I'm going to do before we can set this up is that formula that I just wrote with the squares and all that is not written like a function. You need to solve this for y. So writing this as a function in terms of y, I would write it this way first to get y squared by itself, and then take a square root on both sides. This is how you would solve for y. Y equals square root 4 minus x squared. This is the formula that I want. Now, ordinarily, when you take a square root on both sides, you should consider, do I need to put a plus or minus on both sides? Actually, in terms of the circle, the plus or minus is necessary in order to get the top and the bottom of the circle. But in this example, actually, all I care about is the top of the circle anyway, and so I'm just taking the plus one. If you put the plus or minus, actually, it wouldn't make a difference, but we don't need the plus or minus here because we only want the top half of the circle. All right. Anyway, I think we can plug into our formula now. So now we've done the setup. The volume is, all right, pi. Remember, this is the answer I'm looking for. I'm feeling good about this pi so far, right? There better be a pi in there somewhere. Integral, can anyone tell me the boundary values from here to here? This you should be able to tell just by looking at the picture. Yeah, minus 2 to 2. Those are the the region of x values that I'm talking about here, from minus 2 to 2. And then, remember the formula? F of x squared dx. So I go, f of x is my formula of the function, like that, squared dx. All right, that was the volume formula, volume of revolution. And now we just need to simplify and do the integral. I don't like the looks of this square root with some stuff inside of it, but actually, this squared kind of saves the whole thing. When I have square root and then squared, those kind of cancel each other out, right? The squaring will kill the square root. So this actually just looks like 4 minus x squared. The square root gets killed by the square, and everything is great now. All right, this is now just a simple integration. So when I do the integral, I get 4x and then minus 1/3 x cubed. And I plug in minus 2 and 2. Now, knowing the answer I'm looking for is 32 over 3 times pi. Actually, I like that 1/3 there because there has to be a over 3 at some point. And I'm feeling it with the 1/3. All right, plug the numbers in and hopefully all the numbers will work out. Pi, this is 4 times 2 minus 1/3 times 2 cubed. Subtract. Pi, 4 times negative 2 minus 1/3 times negative 2 cubed. All right. And now, you know, for once in my life, I'm actually going to simplify this just because I know what the answer is supposed to be. I want to make sure this is really what I get. I get pi times, this is 8 minus 8 over 3, right? 2 cubed is 8. So that's 1/3 times 2 cubed, 8 minus 8/3, and then minus pi. This has -8, and then it's going to be a plus 8/3. That's because -2 cubed is -8, which multiplies a -1/3 and gives me 8/3 there. And what is 8 minus 8/3? If I want to add the fractions, I usually don't want to do this, but adding the fractions, 8 would be 24/3, right? And then 24/3 minus 8/3 is 16/3. So this says pi 16/3 minus. And if you notice, the stuff inside the parentheses here is actually the same as the first one, but it's negative. This is negative 16/3. And since those are both negatives, I get 16/3 plus 16/3, which is indeed pi times 32/3. That's the correct answer, right? That's what we said it was going to be at the very beginning. I don't know about you. I find it satisfying that you can actually work out this kind of thing without using the formula, right? You can do this as a volume of revolution. If I really had to know the volume of a sphere, I would use the formula, of course, in real life. But you can figure out, even if you forgot the formula, if the knowledge of the formula was lost to humanity, you could still figure it out on your own. All right? Great. All right. I got a couple more examples, and then some variations. I think I'm ready for the variations already, actually. Let's talk about two types of variations. One is simple, the other is quite complicated. So the simple variation is sometimes we must do it in terms of y. Just like for the area between curves, like what we were doing at the very beginning today. Sometimes just because of how the shape is set up, you have to do it instead of integrating with x, you do it in terms of y. Here is an example of that. Let's look at the volume of, I want y equals x squared, like so. But I'm going to revolve this around the y-axis instead of around the x-axis. So let's go up to 1 here. And then I want to revolve like so. All right? You get sort of like a bowl shape, a parabola-shaped bowl. All right? There's actually a name for this shape. This three-dimensional shape is called a paraboloid. The 3D shapes are often named like oids, paraboloid. There's also a hyperboloid, which is a 3D version of a hyperbola. Anyway, that's called a paraboloid. Let's find the volume of that paraboloid. You have to do this one in terms of y, because this time, when I do the slices, if I slice it like this, like we did in the previous examples, if you slice them vertically, actually those slices don't look like circles anymore. They look like parabolas or something if you cut it up this way. Instead, you should cut it up this way, and they will look like circles. So I'm going to say to get circular slices, we need to slice horizontally, right? This way. If you cut it up that way, you will get the same kinds of circular type slices. If you cut it the other way, up and down, you get weird parabola type shapes, which will not, you can't use the same formula that way. In order to get these circular slices, we have to slice horizontally. So that means the radius this time is given by this horizontal distance. We do everything in terms of y. All right. So that means my formula, when I write my volume formula, it's going to look like pi integral a to b f of y squared dy, right? And when I write my function, it should be x equals something in terms of y. So my, as originally written was this, I translate it into this. Because this is how I would solve for x in that function, in that formula. Y equals x squared. I instead solve for x by taking the square root on both sides. All right? But otherwise, this will work out in the same old way. So here, when I plug this stuff in, it's a pi here, and then it's going to be root y, the whole thing squared, dy. And what are my boundary values? That would be the y value at the bottom up to the y value at the top. And in this example, you can just tell by looking at the picture, it is 0 at the bottom up to 1 at the top. Because I start, the bottom is y equals 0, the top is y equals 1. All right. That's the setup. This one, the integral is very easy to do. What is root y squared? It's just y. The square root kills the square kills the square root. So this is just pi integral y dy from 0 to 1. And then that's y squared over 2. Plugging in 0 and 1, I get pi times 1/2 minus pi times 0. Pi over 2 is the answer. All right. So this was just a simple example of sometimes you have to do everything in terms of y. This is really not a big deal. You just have to rearrange your formulas a little bit. All right. I said I wanted to talk about two variations. One is kind of an easier variation. That was this. A much harder variation, though, is what I'm about to say. Any questions about this so far? Unfortunately, I would say pretty much all the ones that we've done so far have been kind of easy ones. The harder ones involve what we call volumes using washers. Volumes using washers. This is what's necessary for stranger volumes like this. Here's an example. I got this is y equals x, and this, I have a steeper one, 2 lines here. This is y equals 2x. And the volume that I want goes from 0 to 1. I want this much of it. That shape revolved around the x-axis. This can be a little hard to visualize even what I am talking about, this shape. But you take that triangle up there. I'll try and draw it sort of separately over here. It's this shaded in triangle that I drew over there. And then you spin that around the x-axis. And what it looks like is sort of like you'll get kind of a mirror image sort of triangle down here. This is sort of like a big top tent or something if you were to turn it sideways. Or like a cone-shaped hat. It's not a solid cone. It's a cone-like thing that you could like put on your head. All right? This is a weird shape. That's the volume that I want to talk about. So this is a cone-like thing, I guess. If you just say cone, that usually means like just the entire cone. This is a cone with a cone drilled out of the middle of it or something. All right? I want the volume of that cone-like thing. Now, this is fairly different from before, but I again want to think of it in the same terms, and that is if we think of this as being sliced up kind of this way, I'm making vertical type slices here. what do each of the individual slices look like? Here, it no longer looks like much of anything on this picture, but I'm going to try and think about, like, one slice, if it has this curvature to it, if you're going to slice it up a bunch of times this way, sorry for this picture doesn't really look like much, I know, but if you take that thing and slice it up a whole bunch of times and then like pull out one of those slices, I would like to know, what does one of those slices look like this time? They have a little bit of thickness to them, but I would say each of these slices, it kind of looks like a big ring. It has sort of an outer circle to it, but then it has an inner circle which has been drilled out of the middle. All right, so I would say each slice is like, if I were to draw a picture of it, it's like has an outside circle and an inside circle which has been kind of drilled out, and it also has a little bitty thickness to it. All right, it's like that. It's like sort of a ring shape, where this is all solid and it has a hole going through the middle. All right, this is called a washer. A washer, like a a nut goes into a screw. A nut doesn't go into a screw. A bolt goes into a nut, right? And then there's like a washer, which is just like a flat thing that a screw can go through. That's this. This is what the word washer refers to. It's this kind of ring shape with a hole in the middle, right? It's like if you were looking on it straight on, it would be this, right? Only it has some thickness to it. All right? This is what our book calls a washer, or it's like a gasket that has that shape too, right? This is what each shape looks like. Okay, I want to do another kind of formula here by adding up the areas or the volumes of the individual washers. They're not cylinders anymore. Anybody happen to remember from high school the formula for the volume of a washer? The answer is no. We probably never talked about that before. But actually, it's easy to see. The washer is just, it's kind of like the big outer cylinder, but then you remove an inner cylinder from it. So the volume of this washer is just kind of the outside volume, and then you drill out the inner hole from it. So this washer, this has volume. This is actually, remember this like pi r squared h thing, where the h is delta x. It's pi times outer radius squared times delta x minus pi times the inner radius squared times delta x. All right? Where what I mean by outer and inner is, each of these things, that's the outer and that's the inner. It has the radius to the inner circle, and there's also the radius to the outer circle. That's what I call the outer radius and the inner radius. All right? This is the volume of one of these washer shapes. Because the volume of the washer is the same as if I took the volume of the entire thing without the hole in the middle, but then I subtract out the volume of the hole in the middle. That's what all of this is. And now this can be simplified. If you sort of factor the pi and also factor the delta x, you can write it like this. And this is a fairly simple formula to work with. It's like that, right? If I factor both of those things, they're subtracted, but they both have pi in the front and they both have delta x on the end. So we can factor the pi's out of the front and the delta x out of the end, and we just get outer squared minus inner squared. All right? So this is I'm going to write this as an integration formula. So this is the volume with washers formula. Writing this as an integral, it looks like volume is pi, integral a to b, and then we have the outer radius squared minus the inner radius squared dx. All right, and this is the fancier version. You know, I put that other formula in the box. This is the fancier version of that same formula. The one that I wrote in the box before, you could imagine is just the same as this, but the inner was 0. There was no hole in the middle of those circles. Now, if there is a hole in the middle, you've got to use the washers formula. And that's why, like if you look at our big list, the checklist of topics, this thing is called volume using washers or something like that. It has the word washers in it, all right? And you should expect when you're doing the homeworks or something, using the other formula that I put in the box, that's like the easy ones. Most of them are going to look like this, though, where you have to do the outer and the inner separately. And these ones can be quite tricky to set up. So I wanted to do a bunch of examples. Well, can we just do the one that I said before? This specific example right here. So I'm going to write this again. So let's try. I have, this is y equal x. And then I also have y equals 2x. I want to go over to 1 here. That area, and then you revolve it around the x-axis from 0 to 1. All right? Let me get rid of my arrow there. Revolved around the x-axis. All right. We are going to use the formula. Now, just looking at this, I can tell the boundary values are from 0 to 1. So this is not the hard part. We're going from 0 on the left up to 1 on the right-hand side. And then I'm going to do the outer squared minus the inner squared with a dx. So really the only hard part as far as the setup is figuring out what do I use for the outer versus what do I use for the inner. And I think in this example it's not so hard. If I were to maybe draw a bigger version of this picture, here's y equals x, here's y equals 2x, here's the x-axis. What I mean by outer and inner is this distance is the inner, this distance is the outer, right? This is the outer, this is the inner. And those distances are given by the two functions. So the outer is y equals 2x, because that's the formula for that, the line which is higher up. And then the inner is y equals x. That's the other line, all right? So here, the outer and the inner are 2x, like that, minus the inner is x, like that. This is my outers and my inners, all right? This is actually the hard step of doing these problems. This one, in my opinion, is not so hard, but we're gonna get a little fancier as we go. But that's the outer and the inner. All right, can we just finish this off? And then I have one for you to try, and that'll do us for today. I got the pi, 0 to 1, 2x squared. You have to square the 2 and also square the x, so this makes 4x squared, and then minus x squared. I could subtract those and get 3x squared. And then we'll do the integral. So 3x squared, the integral is x cubed, right? So this is pi times x cubed. Plugging 0 and 1. Pi times 1 cubed minus pi times 0 cubed. It's just pi is the answer. All right. The hard part is setting it up. After the setup, you just kind of work out the integral. Is usually not a problem. All right. In our remaining 10 minutes, I got one for you to try. I would like you to find the volume of a similar thing, but it's, instead of that picture, I want the line y equals x and the line y equals x squared. So this is y equals x, this is y equals x squared. I want this region in there revolved around the x-axis. All right. You will have to decide, you're going to use this formula, pi integral a to b Outer radius squared minus inner radius squared. You'll have to decide what's the outer and the inner, and also what's the A and the B. These things you can figure out. See what you think. We got 10 minutes. I think that's enough time.
Start back here. Excellent. So this one, outer. Here's where it's being rotated. And then here. So it should be something there up to the outer. How's it going? Outer minus the inner. So you're measuring sort of the distance we measure from here up to the third or up to the outside. Is it like that? The far one is the outer. How's it going?
Are you supposed to find mass points?
Yeah, you need to find those points for the A and the B.
So you're sending these equal each other?
Yep. Or you could just try to kind of common sense it. Do you know what X number makes it so that X and X squared are the same? Oh, shoot. So, or you could set it up. So, yeah, it's looking good. How's it going? Zero on zero. Yeah, that's good. You okay?
What should we do for that?
Just one top, over series. Yeah, so I got this. So this is just. What are you ready to do? Here's the outer and you think about this is where it's rotating now, and the inner would be the one that's near. Right, yeah, because it's spinning around. This is kind of so this is near. Yeah.
All right, we gotta go, so let's talk about this. I would say the hard part, such as it is figuring out which one is the outer and which one is the inner. remember, you imagine, so here is where I'm rotating around the x-axis, and if I'm at a point there, that's the inner distance and that's the outer distance, right? It's just how far do you have to go from the center up to the, this is, if you think of this solid shape, this is the inner wall and this is the outer wall of the solid shape, all right? So the inner in this example is x squared, right? The curvy part. And the outer is y equals x. So I go pi integral. Outer is x squared minus the inner is x squared, like that. All right? It is the outer squared minus the inner squared. What about the boundary values? I have to go from here to here, and you can figure out what those are in terms of their x values. I can tell the one on the bottom is x equals 0, right? Just because I can see it on the origin. The other one, what is this value right here? You can try to sort of common sense this. I'm looking for a point where x and x squared have the same value. I'm thinking about 1. 1 is the same as 1 squared. So this, if you like by common sense, you can just figure out that's 1. Or if you, for whatever reason, can't guess that out of nowhere, you can find those intersection points by setting these equal to one another. And I would say x equals x squared, and then solve this by factoring. 0 equals x squared minus x, and then factor like that, right? This is how you do it if you tried to work that out by hand, although I hope that you could just sort of notice that the boundaries here are 0 and 1, all right? Anyway, that's the setup, dx. We should simplify as much as we can on the inside and then do the integral. X squared is x squared, and then x squared squared is x to the 4. And now this becomes a simple integral. I get 1/3 x cubed minus 1/5 x to the 5. And we plug in 0 and 1. When you plug in 1, those x's in there become 1s. And I get pi 1/3 minus 1/5, and then I subtract pi 0, 0. So it's pi times 1/3 minus 1/5, whatever that is. All right, this is the washers thing. We're going to do some more, actually slightly even more complicated ones with these next time. That'll do it. Let me know if you got homework questions. I'm happy to chat about it. I mean, we could chat about it right now if you want, or send me an email, or come to my office sometime.